Welcome to this explainer. Let's just dive right in. I want you to imagine you're holding the ultimate recipe book for the entire universe. I mean, every single thing around you right now, your coffee mug, the water you're drinking, the air you're breathing, even the stars, it's all made from a specific set of ingredients. Today, we're exploring KSSM Science Form 1, Chapter 6, which is all about the periodic table and the fundamental building blocks of matter. We're going to decode this cosmic recipe book together, and trust me, by the end of this, you'll see the everyday world in a completely different light. To keep things simple, we've broken our explainer into 4 parts. 6.1, Classification of Elements, 6.2, Understanding Mixtures, 6.3, Understanding Compounds, and a quick chapter summary to wrap it all up.
Starting right off with Section 6.1, Classification of Elements.
Okay, to really understand the universe, we have to start at the absolute smallest scale. We need to look at the tiny units that make up all the stuff we can touch and feel. The most fundamental building block, the smallest unit matter can possibly be broken down into, is the atom. Think about it like this. If you took a gold bar and kept cutting it in half over and over again, eventually you'd be left with a single atom of gold. It's so unbelievably small, you'd need a massive electron microscope just to see it. But crazy enough, that tiny indivisible unit still has all the exact properties of gold. Now, even though the word atom actually comes from an old Greek word meaning indivisible, atoms actually contain even smaller subatomic particles inside them. An easy way to remember them is the mnemonic PEN, protons, electrons, and neutrons. If you look at the center, the nucleus holds the positively charged protons and the neutrally charged neutrons. Then, whizzing around that nucleus in specific shells are the electrons, which are negatively charged. And because the number of positive protons perfectly balances the negative electrons, the whole atom is totally neutral. Here's where it gets really interesting, though. Single atoms aren't always stable on their own. They actually want their outer electron shells to be full. So to get stable, they team up. It's kind of like finding a dance partner. When 2 or more atoms chemically bond together, they form a molecule. Take a single oxygen atom, represented by the letter O. On its own, it's highly reactive and, well, looking for a partner. But when it bonds with another oxygen atom, boom, it forms O2. That's the super stable, life-giving oxygen molecule we're breathing right now. Molecules are basically the smallest chunks of a substance that still act like that substance. Let's build on that for a second. If you have a substance that is made entirely of identical atoms, we call that an element. It doesn't matter if it's a single atom of helium or an O2 molecule made of 2 identical oxygen atoms. If the ingredients are exactly the same, it's an element. But when atoms from completely different elements chemically combine, that's when they form a compound. Water is a great example here. It's a compound made of hydrogen and oxygen chemically locked together to create something totally new. Which brings us to, honestly, science's greatest organizational chart, the periodic table. Instead of just a random jumble of 118 elements, this chart acts like a super organized library. It arranges everything strictly by its proton number. That's just the number of protons in the nucleus. As you read across the horizontal rows, which are called periods, that proton number just ticks up sequentially, exactly like days on a calendar. And the vertical columns, or groups, stack up elements that share similar chemical properties. It makes it incredibly easy to predict exactly how these building blocks are going to behave. In the real world, this is how we categorize what we interact with. We basically divide elements into metals and nonmetals. Think about a shiny copper wire compared to a chunk of charcoal, which is carbon. Metals are usually shiny, ductile, which means you can pull them into wires, and they're awesome conductors of heat and electricity. Nonmetals are pretty much the exact opposite. They're dull, brittle, so they snap easily, and they make terrible conductors. Knowing this lets us pick the right tool for the job, right? Like using copper for a wire and wrapping it in plastic, a nonmetal compound, so we don't get a shock. Moving on to section 6.2, Understanding Mixtures. All right, so we've got the individual building blocks down, but what happens if we put different substances together in a bowl, but we don't force them to chemically bond? Well, we get a mixture. The absolute golden rule here is this. Because they're mixed together physically, they can be separated physically. No new chemical is created. The original substances keep doing their own thing. If you mix iron powder and yellow sulfur powder together, you haven't made a new substance. You just have iron and sulfur casually hanging out next to each other. And because they aren't chemically locked together, we've got 6 primary physical methods to pull mixtures apart. We can use filtration for insoluble solids in liquids, kind of like making drip coffee. Distillation separates liquids that have different boiling points. Separation using magnets is super easy. Just pull that magnetic iron right out of our sulfur mixture. Sedimentation is just letting heavy stuff sink naturally to the bottom of a liquid over time.
Flotation separates things based on what sinks and what floats. And chromatography is this really elegant way to separate tiny amounts of mixtures, like pulling apart the hidden colors inside a single drop of black ink.
Now for section 6.3, understanding compounds. Okay, but what happens when elements actually do link arms chemically? This is where chemistry gets a bit magical. A compound is created when two or more elements mix chemically. Unlike a casual mixture, real chemical bonds are formed here, and it creates a completely new substance. And here's the wild part. The new compound has completely different properties than the raw ingredients that went into it. For example, sodium is a metal that literally explodes in water. Chlorine is a toxic gas, but bond them chemically, you get sodium chloride. That's regular table salt, a compound you happily sprinkle on your fries. And the cool thing is, there are super predictable patterns to this chemical magic. If you combine a metal with oxygen, you'll always get a metal oxide. Magnesium plus oxygen equals magnesium oxide. If you mix a metal with water, it gives you a metal hydroxide and releases hydrogen gas. And if you heat a metal with sulfur until they bond, you get a metal sulfide. Remember that loose mixture of iron and sulfur we talked about? If you actually heat it up, it permanently transforms into iron sulfide, a totally brand new compound. Because compounds are locked together by strong chemical bonds, you can't just weave a magnet over them or use a coffee filter to separate them. With that iron sulfide, a magnet won't pull the iron out anymore because it's permanently attached to the sulfur. To break them apart, you need chemical intervention. A classic example is electrolysis. This is where we zap a compound, like water, with a strong electrical current to forcefully break those bonds, splitting it back into pure hydrogen and oxygen gases. To really bridge the gap between mixtures and compounds, we have to look at physical versus chemical changes. A physical change alters the state, but it's still the same stuff. Melting an ice cube just turns solid water into liquid water. It's still H2O, which relates perfectly to our physical mixtures. But a chemical change forms a completely new substance. When iron reacts with oxygen to form rust, or when leaves decay in the woods, those are major chemical changes, producing brand new compounds with totally new properties. Let's actually put these two side by side to really lock it in. Mixtures are purely physical. They create zero new substances, they can be separated by easy physical methods, and they keep their original properties. Compounds, on the other hand, are strictly chemical. They create brand new substances, they require intense chemical separation methods, and they have entirely different properties than what you started with. If you grasp this difference, you've pretty much nailed the core of Form 1 chemistry. Let's wrap this up with a quick chapter summary. We've gone all the way from invisible microscopic particles right up to the stuff we interact with daily. Here is the exact sequence to lock into your memory. Step 1, subatomic particles, protons, neutrons, and electrons build atoms. Step 2, when you have a bunch of the exact same atoms, you've got an element, neatly organized on the periodic table. Step 3, mix different elements together physically, and you get a mixture. Step 4, when those elements form strong chemical bonds, they transform into an entirely new compound. So, here's what I want you to do. Look around wherever you are right now. The air you're breathing, is it a compound or just a physical mixture of gases? What about your water glass, your phone screen, or the keys in your pocket? Which ones are physical mixtures just casually sitting together, and which are complex chemical compounds locked in an atomic embrace? Once you start looking at the world through this lens, the recipe book of the universe is just sitting there, waiting to be read. Thanks for joining me on this explainer, and keep exploring.